Hey guys, I'm going to be going over some of the notes for chapter 9. I'm starting kind of in the middle, so make sure you go through all of the notes. And this is just going to cover all of the problems that need to be worked out. So in this chapter we're discussing the relationship between different properties of gases. Gas laws are mathematical relationships between the volume, temperature, pressure, and amount of a gas. So volume is measured in milliliters or liters. It's how much space something takes up. Pressure, it talks about at the beginning of the notes. Units are millimeters of mercury or torr. These are the same thing. They're equivalent, or atmospheres. And then, as I said before, 1 atmosphere equals 760 torr, or millimeters of mercury. Temperature, we're used to temperature, but usually what we see is temperature in degrees Celsius. But we're going to talk about how we always need to convert this to the unit of Kelvin. And then the amount, which is N, is moles. And so we're always going to refer to amount when we're talking about gases in terms of moles. So first, the relationship between pressure and volume. The law that describes this is called Boyle's law. If a fixed amount of gas is kept at constant temperature, so we're taking temperature out of the equation by keeping it constant, then pressure and volume are inversely related. And so that means that as you increase the pressure here, then the volume decreases. Or as you decrease the pressure, the volume increases. And so small pressures have a large volume, large pressures have a small volume. And so you see, if you have a piston full of air, if you compress that and you decrease the volume, you increase the pressure by having a smaller surface area for these molecules. And so the relationship between this is that the pressure times the volume is equal to a constant. And so then if you change one of the values, then that pressure times volume is going to keep equaling that constant. And so you can come up with this equation here by changing one of the values to see what the other value would be. And so if you change the pressure, you can figure out what the volume would be. Or if you change the volume, you can figure out what the pressure would be. For example, here it says the sample of oxygen gas has a volume here of 150 milliliters. So that would be our volume 1. When its pressure is 0.947 atmospheres, that would be our pressure 1. What will the volume of the gas be? So what will V2 be at a pressure of 0.987 atmospheres? That is P2. So what we're looking for here is we're trying to solve for volume 2. Here is our equation. We want to isolate V2, and so we would divide both sides by P2. So we get that V2 equals P1 V1 over P2. V2 is going to equal P1, which is here, 0.947 atmospheres, times V1, which is 150 milliliters. Decimal is important for significant figures. And we're going to divide by P2, which is 0.987 atmospheres. So what we're doing here is increasing the pressure, so we're going to expect the volume to decrease because it's an inverse relationship. Here you can see that the units cancel to give you milliliters. So in my calculator, I'll do 0.947 times 150 divide by 0.987 And we should get, I get 143.92, which to 3 significant figures would be 144, and my unit is milliliters right there. I'm going to work that out one more time just to make sure it's correct. Okay, and that makes sense that the volume's decreasing as the pressure increases. So the next law is between temperature and volume. So if we keep pressure constant, then the volume and the temperature are directly related. So that means that as you increase one, you increase the other. High temperature, high volume, low temperature, low volume. This only works, however, if temperature is in the units of Kelvin. So we're going to talk about what Kelvin is. Kelvin is a unit of temperature in which 0 actually means 0. Right now, if you're talking about degrees Celsius, 0 does not mean the coldest it can get. It can get lower than 0 degrees Celsius. You cannot get any lower than 0 degrees Kelvin. You really haven't gotten there. It's just an extrapolation to actually get there. But it is at negative 273 degrees Celsius is absolute 0. And so when we're talking about the relationship between temperature and volume, we're talking about that in terms of Kelvin, which doesn't have any negative numbers. 0 is 0, and then everything above that is a non-negative number. And so to get from Celsius to Kelvin, you will add 273.15. So that is the formula to get from Celsius to Kelvin. And so the difference between Kelvin is that it's 273.15 degrees Celsius higher than any degree Celsius that you are given. And so if a gas is kept at constant pressure, this is going to be our gas relationship between volume and temperature, because as one increases, the other increases. So it's this relationship here to represent that direct relationship. So if a sample of neon gas occupies a volume of 752 milliliters at 25 degrees Celsius, so here is our V1. Here is our T1, but we're going to have to convert that to Kelvin. What volume, so what V2 will the gas occupy at 50 degrees Celsius? Here is our T2, but we're going to need to convert that to Kelvin if the pressure remains constant. Okay, so I'm going to first take T1 is going to equal 273. I'll just write that instead of 0.15 just because it's easier, but you can do either one is fine. 298. Okay. And so that is our T1. And then T2 is going to equal 273 plus 50. So that is 323. Okay. I'm going to assume that that is a decimal there to make that easier. And so now we want to know what volume is V2. So we want to isolate this value. And so in order to do that, I'm going to multiply both sides by T2. And so V2 equals T2 V1 over T1, which is going to equal T2, which is 323K, times V1, which is 752 milliliters, over T1, which is 298. Okay. And so here what we're doing is increasing the temperature, and so we are going to expect the volume to also increase. So we want it to get bigger. So 323 times 752. Divide that by 298, and I get 815.087. 3 significant figures, so 8, 15. Kelvin cancels, end up with milliliters. So the volume did increase, so that number looks right. You have increased the temperature, so you've also increased the volume. The last one would be volume and moles. If a gas is kept at constant temperature and pressure, volume and moles are also directly related. And so if you keep it at constant temperature and pressure and you increase the number of moles, you're going to increase the volume as well. And so increasing the volume, you would have to add something to that. And so if 2.45 moles of argon gas occupy a volume of 89.0 liters, so here is our N1. A volume of 89.0 liters is our V1. What volume, so this is V2, well, 2.10 moles of argon, so N2 occupy under the same temperature and pressure. And so here's our equation. N1 over V1 equals N2 over V2. And so we want to know what the volume is. And so I'm going to cross multiply here. N1 V2 equals V1 N2 divided by this. So V2 will equal 89.0 liters times our N2, which is 2.10 moles, divided by N1, which was 2.45 moles. And so what we're doing here is decreasing the number of moles. So we're going to expect the volume to also decrease. 89.0 times 2.10 divided by 2.45 equals 76.286. 3 significant figures would be 76.3. Moles cancels there. I end up with 76.3 liters. So the volume did decrease along with the number of moles. Okay, next gas law. The ideal gas law is something that does not deal with changes. These other ones dealt with changes if we're changing something. This just relates to a gas in a container with no changes. So this relates all of these units together. It says that the pressure times the volume is going to equal N times a gas constant, which here is 0.08206 liter atmosphere over mole Kelvin, times the temperature. And so the important thing here is if we use this constant, the units have to be liters, atmospheres, moles, and Kelvin. And so if we're given something in torr, millimeters of mercury, we need to convert that to atmospheres. If it's something other than liters, we need to convert it to liters. But here is our ideal gas law. So to use this, what is the pressure in atmospheres exerted by a 0.500 mole sample of nitrogen gas in a 10-liter container at 298 K? So here is our N, here is our V, here is our T. Our R is 0.0826 liter atmosphere over mole K. And so this is going to be our equation coming from the ideal gas law, just dividing by volume. And so P equals 0.500 moles times 0.8 or 0.8206 liter atmosphere over moles Kelvin times the temperature, which is 298 K, over the volume, which is 10.0 liters. So I've got moles, Kelvin, liters. If I put all these together, the moles will cancel, Kelvin will cancel, liters will cancel. You'll end up with atmospheres. So now I just have to make sure I put this in my calculator correctly. So 0.5 times 0.08206 times 298, equal that out, divide by 10, and I get 1.22269, and I want 3 significant figures. 1.22, atmosphere is my unit. So you want to make sure you're showing all the units cancel when you're doing this problem. This will help you make sure that you're doing it correctly. So I'm just going to redo this real quick to make sure I'm not giving any of you the wrong answers. Okay. If you ever see me do something with the wrong answer, just send me an email and I will correct it. Okay, the next one. What mass of chlorine gas? Okay, so we're not going to be able to get mass, but we can get moles. So we're going to have to start with moles here. Is contained in a 10-liter tank. So here's our volume. At 27 degrees Celsius. Here's our temperature, but we're going to need to convert that to Kelvin. And here is our pressure. And so here, first, temperature equals 273 plus 27. And so that's going to be 300 K. N here. So this is coming from PV equals nRT. You divide by RT right there. And so I'm looking for N so that I can then go to grams. And so N is going to equal our pressure, which is 3.50 atmospheres, times our volume, 10.0 liters, divided by our rate constant, gas constant, 0.8206 liters atmospheres over mole Kelvin, times our temperature, 300 K. Atmospheres cancels, liters cancel, Kelvin cancels. I'm going to put moles in the denominator, which would switch to the top because it's in the denominator. Now I've got 3.5 times 10 divided by 0.08206 divided by 300 equals 1.42 moles to 3 significant figures. One more time. Divided by 0.08206 divided by 300 equals 1.42. Okay, so this is how many moles of chlorine gas we have. We want to know grams, so then I'm going to do how many grams of chlorine equals 1.42 moles of chlorine. Moles of chlorine to grams of chlorine. This is 2 times 35.45 because that's what the mass of chlorine is. So 2 times 35.45, 70.90. So then times 1.42 equals 100.678. We want 3 significant figures, so that rounds to 101 grams of chlorine gas. So first I found moles, and then I converted that to molar mass. Okay, one more law. Dalton's law says that for a mixture of gases, the total pressure is the sum of all the pressures that each gas would exert. So this is pretty self-explanatory. The total pressure is going to be whatever pressure of each gas in that container is. And so here, if you have 1.75 moles of helium, if you have 0.75 of hydrogen, 0.75 of helium, 0.25 of neon, it's going to be the same total pressure. So all these are going to add up to equal the total pressure in there. And so if you're collecting a gas over water, then you're going to have some vapor pressure. And this is where Dalton's law is most important. So the pressure in the total is going to be the pressure of the gas plus the pressure of water. So when you're collecting a gas over water in this setup here, you would have to subtract the pressure of water from that in order to figure out the pressure of the gas. And so here you would use the vapor pressure of water as a function of temperature at that temperature. So if it's at room temperature, you know that this is how much pressure of water would be above that solution. This is the vapor pressure, so that's how much a constant amount of how much water is above a amount of liquid water at any given time. And so here, this problem, oxygen gas from the decomposition of potassium chlorate was collected by water displacement. The barometric pressure and the temperature during the experiment were 731 torr and 20 degrees respectively. What was the partial pressure of the oxygen collected? And so the pressure here, barometric pressure is 731 degrees torr. So 731.0 torr is going to equal the pressure of oxygen plus the pressure of water. So it's 20 degrees Celsius. At 20 degrees Celsius, here is the pressure of water. It is 17.535. And so for the pressure of oxygen, all I'm going to do is take 731.0 minus 17.535. These are both torr. And so 731, 17.535 equals. So in one place past the decimal, I get 713.465. But I can only keep one place past the decimal. So I get 713.5 torr as my answer. So that is the pressure of oxygen above the water. Okay, one last thing is standard temperature and pressure. So these are things that are defined. And so the standard conditions scientists have agreed upon to compare volumes or amounts of different gases. And so if they say we have this amount of a gas at STP, it means it's at 1 atmosphere. You can assume it's 1.000 atmosphere and 0 degrees Celsius, which would be 273 K. And so here, for example, if a chemical reaction produces 0.0680 moles of oxygen gas, what volume in liters is occupied by this gas sample at STP? So here's our N. Here is our volume. Our pressure will be 1 atmosphere. Our temperature will be 273 K. And what we want is our volume. So we've got PV equals nRT. We want to isolate volume. And so we get volume equals 0.0680 moles times our gas constant, 0.08206 liter atmosphere over mole Kelvin, times our temperature, which is 273 K, over our pressure, which is 1 atmosphere. So atmospheres cancels, Kelvin cancels, moles cancels, and then we get 0.0680 times 0.08206 times 273 equals that divided by 1, which won't change anything, and so I get 1.523 liters. I'm going to do this again to make sure. 0.08206 times 273 equals 1.523 liters. I want 3 significant figures, and that is my answer. Okay, last one is relating this to some stoichiometry. Let's look at this first one here. What volume of chlorine gas at 38 degrees Celsius and 1.63 atmospheres is needed to react completely with 10.4 grams of sodium to form NaCl? And so here they're telling you an equation here. The first thing that we're going to need to do is come up with that chemical reaction. And so for number 1, the chemical reaction would be that sodium reacts with chlorine gas. And so you may not remember this, but I've talked about before that chlorine always exists as Cl2. And so sodium reacts with chlorine gas to form NaCl. I'm going to balance this. Put a 2 right there and a 2 right there. Okay, so that is our chemical reaction. We want to know the volume of chlorine gas, and then they give us this. But then they tell us that we want it to react completely with that much sodium. And so what I'm going to try to do then is get the moles of chlorine that would need to react with it, then plug it into the ideal gas law to figure out the volume. So first I'm going to say how many moles of chlorine gas would be needed to react with 10.4 grams of sodium, grams of sodium, moles of sodium, and then I'm going to go from moles of sodium to moles of chlorine. And so that would be a 1:2 ratio. Here's 1, and then 22.99 for sodium. And so I've got 10.4 divided by 22.99 divided by 2 equals 0.226 moles of chlorine would be needed to react with that. Do that one more time. 10.4 divided by 22.99 by 2. Okay, so that's how many moles of chlorine. So now I can figure out, by the ideal gas law, PV equals nRT. I can solve for volume. Divide by pressure, divide by pressure. So the volume will equal the moles, 0.226 moles, times 0.08206 liter atmosphere for mole Kelvin, times temperature, which is 38 plus 273 equals 38 plus 273 equals 311. Divide by the pressure, which is right there, 1.63 atmospheres. Atmospheres cancel, moles cancel, Kelvin cancels, end up with liters. And so 0.226 times 0.08206 times 311 divide by 1.63 equals 3.54 liters. So that is how many liters of chlorine would be required to react with all of the sodium. Okay, I'm not going to work out this problem, but I'll look at it. How many liters of gaseous carbon dioxide, 27 degrees Celsius in this atmosphere, can be produced from burning 65.5 grams of carbon according to the following equation? And so this would be the same thing. You'd be looking for how much carbon monoxide is formed from this much carbon. You figure out the moles, plug it into the ideal gas law, and then you would figure out the volume. So go ahead and work that on your own. If you need to make sure it's correct, then feel free to email me for the correct answer. Okay guys, this is the end of this chapter. There are some more notes, so make sure you go over that. Let me know if you have any questions at all. Thank you. Bye-bye.